In this problem, we are looking at some properties of how to play with the outer measure of subsets of the real line, okay? And the beauty of the fact that the rationals are dense everywhere, as well as the properties of series of real numbers. So let's start with the first one. The first one says we want to show that we have a subset A in R, and we assume that its outer measure is not equal to 0. Okay? So we want to show that for every A in A, there exists a B in A such that B minus A is irrational. So it doesn't belong to Q. Okay? The complement of Q, irrational. So assume not. Then there exists an A in A such that for every B in A, B minus A is rational. Therefore, A is a subset of A plus the set of rationals, which tells us that A, the measure of A, is less or equal to the outer measure of A plus Q. And since the outer measure is in translation invariant, this is equal to the outer measure of Q, which is 0, which implies that the outer measure of A is equal to 0, which is our contradiction. Okay? Since the outer measure of A is positive, not equal to 0. For the second problem, we want to show that, so first of all, we know that Q is countable, and therefore we can put all the rationals, we can enumerate them as Rn, and now we consider the set, let's call it A, which is the union of Rn minus 1 over n squared, Rn plus 1 over n squared, n greater than 1. So it's easy to see that A is open, of course. Okay, and what happened is we are going to show that in fact A misses some real numbers. In other words, that R is different from A. A is a subset of R, but R is different from A. Note that A contains all the rationals. All the Rn's are in A. In other words, that we have Q is a subset of A. So whatever A misses must be irrational. Okay? So assume not. So meaning that R is equal to A. But the outer measure of A, using the subadditivity of the outer measure, is less or equal than the sigma of the outer measure of every interval. Rn minus 1 over n squared, Rn plus 1 over n squared, which is equal, because the measure, the outer measure of an interval is its length, sigma of 2 over n squared, okay, which is finite. Okay, and this is our contradiction because we know that the outer measure of R is infinite, and this is our contradiction.